Great. So next we are doing lightning talks. Today we had, unfortunately, one of our lightning talk members is unable to join us, Meredith Goins, but her slides will still be on our agenda. So please check those out. But we have Jamie filling in for her. So he will go up last. But first we have Shawna Sadler. So please come.
So yesterday you heard me blather on about the high level introduction to ORCID. So today I promised you I'd go just a little bit more specific. So it's a little more relevant specifically to facilities. So I had a few people ask me just to clarify, yes, ORCID is a nonprofit organization. We are registered in the US, but we do have members around the world, and we've been accepted across all subject disciplines. So it's wonderful. Keep it moving. So as I mentioned yesterday, just a quick recap, we issue a unique ID number to a human being. We've talked about lots of different data points these last couple of days. We just do humans. We let other paid organizations do other parts of the research data. We issue the record that I showed you, Eva's and mine, and then we have APIs to exchange the data between different systems. So just to give you a sense of our scope. So like I mentioned, we have researchers that have adopted ORCID in every country in the world. We had some small islands in the North Atlantic that were holding out on us, but we finally got them last year, probably due to all of you here. So thank you very much for that. So we have member organizations. Those are usually universities, funders, publishers in 57 countries around the world. And some countries have so many members, we formed a consortium just to help manage the administrative side of them. So the consortium countries are in green. And I should change this map because, as I was mentioning to Julio earlier, we just started a consortium in Latin America and the Caribbean. And so there's a huge uptake down there, which is really exciting. So we have about, I think we've issued about 12 to 14 million ORCID IDs in we're going on 11 years now, but we can see that only 8 million are active. So some people start and they don't want to do it, or they've accidentally created 2 or more. It happens. And so they can deprecate their old ones to pick their priority. So we've got 8 million active records. Organizational members were just under 1,400. And I was mentioning to you, that diagram with all the interconnected systems. So we're about almost at 5,500 systems that we've connected to the ORCID registry. So we're exchanging data all over the place. It's fantastic. In fact, I want to heat map our registry at some point because I think it'd be a really fun show. There you go. There's the interconnectedness that I mentioned yesterday. Okay, so for research facilities, at the moment, we have 27 research facilities that are active members of ORCID. 3 of them are really writing data. The rest of them are gently talking to us about it and figuring it out. And as the NSF develop their policies and the other funding agencies around the world, we'll get more research facilities that are active. But there's a lot of interest. We only have 3 that are really active right now. So those 3, I don't know if you can read it on that screen. It's a little EMSL, Oak Ridge National Lab, and Access that we talked about yesterday too. So you can see the data that they've been writing has varied over the years. So we've got about 2,000 records with research resources, and I'll show you that in a second. And then many of those have multiple research resource entries. So lots of people have multiple entries. So we've got about 3,000 entries for research resources. So here's an example here. I grabbed an example from Access. So what we do in the ORCID record is we have very minimal requirements for the metadata, and we really let the facility decide what kind of data they want, what's useful for them in the ORCID record. Because really it's thinking about that interconnected infrastructure and who's going to be requesting that data and how it's going to populate those systems. So it's funders asking for your activity with research facilities, publishers, universities, or whoever is exchanging that data. So you can tell in this one, there's the primary, the top metadata, and then you can see below there's sub metadata. So there's a hierarchy that they've created with their metadata. And usually it's facilities and instruments, but it really depends on how the facility is coordinated. So just quickly, the workflow. This is a high level workflow. There are not any vendor systems that have built in this workflow yet. So those 3 facilities that I mentioned that are using this workflow have created custom systems. So, if CI Compass is looking for a project, developing an administrative data system that would include some of these points would be really useful. And that's what we're hearing from a lot of the facilities, especially the smaller to the mid-size. So first, when a researcher applies to use your facility, they log in with their ORCID ID and they share their ID with you. And so this is your way of knowing who exactly this person is, because some researchers have the same name. Second, it goes into a review step administratively. Someone at your facility reviews this application. Sometimes there's a peer review step here at this point too. If you'd like to recognize your peer reviewers you can also write that to their ORCID record. We support both open and blind peer review in ORCID records. So that's something that sometimes if you need to encourage people to be your peer reviewers. Actually, I've heard the opposite from research facilities, that there's so much love for you guys that you can't get your peer reviewers to go away. So, but whatever works for you, we're here for you. And then second, when you approve this brilliant application, you write that data to their ORCID record. Now, what happens is in this workflow, there's a cookie that's been created. I should call it a token. Let's call it a token. And in that token is all the data in this workflow. When they created this relationship with you, what permissions you gave them or they gave you. So they've allowed you to read, write, and update their record, which will come in handy in a moment. So the metadata that you've written to their ORCID record will be there in perpetuity, unless you decide to update that data or the researcher who owns that record decides to delete that data, which is their right, but they cannot edit the data that you wrote to their record. So that data stays in their record in perpetuity. So when systems like NSF Science CV system, they've got a form called current and pending other support forms. So in a couple months, they are currently working on pulling the research resource data that have been written by research facilities into this form to populate what they call the in-kind section. So the non-financial support that the researcher has received. And then that way the researcher doesn't have to enter that data, your data, probably incorrectly. So this way the correct data flows. And then ORCID pre-populates that form and then it goes on for review. So again, the interconnectedness. So here's an example from EMSL. Again, you can see the structured data that they've added. We've talked to EMSL and the Joint Genome Institute, and they are going to be editing that data. Now they've been trying it, right? They've been learning about what works, what doesn't work, and they're going to be fine-tuning the data that they've entered. And same here for Oak Ridge National Lab and their Beam Time Awards. So quickly mention, I'll just say again, one of the new efforts with ORCID is that when a member writes the data, we give them this trust marker. We call that the green check mark, the validated data. And I've had some of you approach me and say that that could actually be really helpful for some of your administrative workflows. I mean, we're all human. We need help with identifying the proper researchers from some of, I like to call them quirky turkeys that approach us, who would ask for huge amounts of money or access to our facilities. You got to identify them and you need tools to help separate those, from the professional researchers. So when your facilities write data to the ORCID records, particularly of the early and mid-career researchers, you're really helping them build that substantive profile so that when they do approach facilities or publishers or funders, they can see that they are a proper researcher and that you've trusted them, and that helps build their profile. Okay, so just quickly, some of the benefits to you and your staff, the facility administrators. What's most important we've talked about is when you structure the data with persistent identifiers, and ORCID is the persistent ID for people. When you structure the data, so it's clear of who this person is, you make the data more precise, but you're also helping make the data interoperable with external systems, right? And we're really talking about administrative data, not your research data here. But that is what really helps move the data forward, and the data is more accurate and timely when the systems can interoperate, and it requires less human time because your humans have better things to do than data entry. I mentioned the tokens that you get when you create that relationship with your researchers and their ORCID ID. So going forward, you can use that token and the API from ORCID and say, you know what is this person doing? Like, what have they published? What funding have they got? Or you can even look for, your facility ID and see what publications and funding your facility ID have been attached to. So you can use ORCID to pull that data, and then you can analyze and then report on that. So it's a really powerful tool. So universities have a hard time following their graduates, their alumni. They're using ORCID for that reason. And so if you think about your researchers in the same way. And then when you create those reports, you really are able to articulate your return on investment to your stakeholders. We all have stakeholders. We all report to somebody. So we need to demonstrate the value, and ORCID can give you that data. So you can say, we had this number of researchers who gave us funding from these organizations. They were from these different countries. Because you want to talk about your global interactions. And these are the publications that came out of our facility. So it's all really powerful, and all those citations should have PIDs so that you can get to really specific funding and really specific articles and data sets. All right, and benefits to researchers. I think I don't need to go. I'll leave that here for you all later. And so then here is when I talked about Science CV and the current pending other support form. So here's just a quick example. So the research resource section in the ORCID record will pre-populate. I tried to do a screenshot of the form here. So it'll pre-populate most of that data. There is some data that's free text that the researcher will have to populate, but the factual data will be pre-filled, which will be really helpful. Okay, so these are some just value statements that we've generated. So if you'd like to use them internally to help pitch ORCID, if you like, in-house. So this is some of the value statements for facilities, value statements for researchers. So feel free to grab these from my slides, reuse them at will. Don't ask for permission, just go for it. Thank you.
Next up is Renaine. And now it's function.
Okay, thank you. Short people problems. Hi, my name is Renaine. I'm a librarian at Florida State University, and I'm here to talk about a project that some colleagues and I are working on. It's an NSF funded project called Increasing the Discoverability and Traceability of Research Facilities and Instruments Through Persistent Identifiers. So we just heard about PIDs for people. Now we're going to hear about PIDs for research facilities and scientific equipment. This is a project that's a collaboration between 4 different organizations. The lead PI, Matt Marinick, a lot of you probably know him. He works at NCAR, and he's leading this project. We are working with UC Boulder Libraries, Florida State University Libraries, and also Stanford's Office of Research. And all of this is tied together by a guy named Claudius Mendoza, who some of you may know, but he sort of connected the libraries with the research for the core facilities groups here at Florida State and also at UC Boulder, UC Boulder and now at Stanford. So sort of the origin of how this project started. More detailed, some of the goals that we're trying to accomplish is we want to create and facilitate an RCN. And it's going to be focused on the assignment of PIDs to facilities and instrumentation. We want to sort of aggregate and put together different use cases, potential and existing, on how PIDs can be assigned and how they can help facilitate open science, save money, showcase the impact of research facilities, things like that. We also want to facilitate the generation of ideas and expertise, and also guidance on key topics of interest around this area. Things like metadata creation, things like what is and what is not a scientific instrument for the sake of PID assignment. Those are some of the things we want to learn more about by engaging with community experts like this group. And then at the end of our 3-year project, we want to, we will provide recommendations and lessons that we've learned throughout the process, and provide recommendations for all the different communities that are engaged in this. So we have facility operators and directors, which is one group. We have the PIs and users who use the instruments in the facilities. We have funders, policymakers, all kinds of different folks who have different ways that they can contribute to sort of streamline the adoption of this stuff. This work's been happening at all of our different, the 4 different institutions in some way or another. Most recently, Stanford is trying to assign RIDs to shared instrumentation and also core facilities. Here's examples here of NCAR and UC Boulder on the assignment of PIDs to specific instruments. Almost 10 years ago, or maybe even 10 years ago at Florida State, there was a push, and this predates me working there, but there was a push to sort of catalog different scientific equipment at the university so that it could be found, so that it could be used by other researchers. And the libraries were involved in that process. And we sort of built a catalog and eventually created a product called Used It. That's sort of a few examples of PIDs and sort of the assignment of persistent identifiers for research facilities. But this is a summary of some of the work that we've done in our first year. So that we sort of, we've about 14 months into this project. And so the things that we've done, spent the first couple of months just compiling resources, information, engaging with our advisory board, a couple of who are here in attendance. We built a project website, put together different documents, and we also went to different conferences. We went to the Association of Biomolecular Research Facilities, the American Meteorological Association, different kind of groups with different stakeholders that have a vested interest in this kind of work. And we did a lot of focus groups. Below, I've listed a few of the different people we engaged with, including earth science facility users and providers, campus facility staff, particularly core facilities at Florida State. We had a focus group with the Highfield Magnetic Laboratory, which you all heard some about their FAIR data work yesterday. And all of that work sort of accumulated with the workshop in Boulder in September. And during that workshop, we had about 30 folks that joined us. And we had people from academic institutions, labs, nonprofits, librarians, and some folks from private industry that were all interested in this space. The way it was sort of organized is we had different, we had panels very similar to this conference where we introduced ideas and topics, use cases, work that's already being done in the area. And then between these sessions, we would have breakout groups that were conducted like focus groups. And we would ask questions about challenges, issues for adoption, benefits for their community. And we recorded that information. And we've been working on a report that we're going to distribute really soon. We've actually sent it to our advisory board, and they're looking over it now. So we'll get some engagement from them and some good ideas. And we're really looking forward to sort of continuing to engage this community because we think there are a lot of opportunities specifically with, the facility directors because the benefits are kind of clear because it's important to track impact and to be able to show how dollars are being used and stretched. And this sort of PID assignment helps because it's easy to cite and pay attribution to the use of those facilities if all the things that are supposed to work are in alignment. What I'm going to do now is actually work through a couple of the primary observations that are in the workshop report that'll be coming out soon. The most basic finding is that there is a stated need for PID assignment for research instruments and facilities. That was stated by folks that attended the workshop. Reasons for this were reproducibility, data provenance, credit for instrumentation developers and providers. Another observation is that the use of PIDs for instruments is a little scattered and in how and which ones are being used. There's multiple PID systems being used for the purposes of identifying research instruments and facilities. Another observation is, at least right now, from what we've heard from the community, is that deciding which PID system to use isn't as important to lowering barriers for adoption for the ones that already do exist, which makes a lot of sense. And then four is metadata. Sometimes changes in metadata are more appropriate to figuring out some of the nuances in the question of what is and what is not instrumentation. A couple more things we found related to instrumentation specifically is the granularity and evolution of these tools. So I think someone earlier mentioned, I think it was research vessels, where they're sort of stock vessels that are the same, but over time they have different specifications and modifications that make them really different. So for a lot of reasons, we want to track the differences between those. Resource limitations is a common theme for the assignment and adoption of PIDs. It's extra work for everybody, so somebody has to do this work. And then convincing users and PIs of the value of citing PIDs for instruments is important, and sort of speaking to some of the higher and more loftier goals around open science and reducing barriers of access to information and streamlining the discovery of new ideas. And then last is just sort of a lack of shared understanding among different stakeholders and incentives and who benefits what and sort of speaking each other's language. So sort of wrapping up, some of the main challenges that we distilled from our focus groups, our reading, and our workshop from this year, last year, I'm sorry, is that culture change is something that we have to be mindful of, this our research group, and that it's going to be important to create like a widespread norm around the citation of research instruments and sort of the paying of attribution for their use. And creating that sort of citation or scholarly community is going to take a lot of time, but it's important. We have to take it one step at a time. Policy change is important. Funders, institutions, and others can adopt policies and make tools and workflows that sort of facilitate the adoption of PIDs and make it easier for users to cite the facilities that they use. And then institutional change. A lot of this starts at university or lab level. This involves identifying sort of barriers to adoption, creating training, resources, thinking about capacity, getting funding, other ways to sort of do this kind of work. So those are the main challenges to adoption. These are sort of what do you think questions, not necessarily meant to be answered right now because this is a lightning talk. But I want to know, at least today and over time, we do your point of view, some of the use cases or benefits for PID adoption, specifically for facilities. And then what do you think some of the challenges and barriers are from your point of view? This is how you can stay connected with our work, and thanks.
Next up is Jim Basney. And look to
Okay, thank you. Hi, everyone. I am PI of TrustedCI, and in my lightning talk, I'll give you a brief update from our project. TrustedCI is the NSF Cybersecurity Center of Excellence, and our mission is to support NSF facilities and NSF projects in developing the security programs that support scientific discovery, the mission of the organization. TrustedCI is a distributed center across multiple organizations. I work at the University of Illinois. I'm joined here by co-PIs. Sean Peisert is at Berkeley Lab. Kelly Shute is at Indiana University. So if you haven't talked with us yet, please do find us before you make your way to the airport. We're happy to talk with all of you. So we have in our name TrustedCI. We want to support the cyber infrastructure that is trusted by the scientists. That cyber infrastructure is essential to the scientific discovery that's at the basis of the mission of NSF. Scientists are trusting that that cyber infrastructure is accessible and available to them when they need it, that it is providing the accuracy and integrity that they expect that's specified in the service level agreement of that cyber infrastructure, that it's respecting their data policies like embargoes and other data protections around the scientific data, and that it's complying with appropriate obligations and regulations for that cyber infrastructure. So we need cybersecurity programs that effectively address the threats to that trust, the threats to those expectations from the scientists, and that produce the artifacts that build that trust with the scientists so they can see that our cybersecurity programs are effective at meeting their expectations. One of those risks or threats is the ransomware risk that continues to be a threat to our cyber infrastructure through attacks like phishing attacks. You can find multiple resources at our website at this link here about examples of ransomware attacks to scientific facilities and some recommendations about protecting your facility against phishing attacks and other attacks that are prelude to ransomware. As Mike mentioned this morning, multi-factor authentication is a real key component of protecting your cyber infrastructure from these attacks. We've had really good discussions this week about how cyber infrastructure is both IT and OT, the operational technology that includes the sensors and the telescopes and the interferometers and all the other pieces that are connecting to our data services to support that scientific discovery. And the cybersecurity of both sides, the IT and the OT, is really critical to providing that trustworthy cyber infrastructure. So Sean led a challenge in 2022 looking at operational technology security with participation by multiple organizations that have their logos listed on the site there. And that annual project published 2 reports with findings and recommendations that I think are still very applicable to the facilities as you address these cybersecurity challenges of connecting your OT to your IT. One of the lessons learned of that OT focused effort in 2022 is, I expect it'll come as no surprise, that adding cybersecurity to the device when it's in the field is a lot more difficult and more costly than building cybersecurity in at procurement time, at development time, at design time. And so in 2023, Sean led an effort called Secure by Design, working with NSF Major Facilities in how to get cybersecurity to be a stronger component of that design and procurement process. And so that included a focus on the maritime domain with input from RCRB and USAP and CCRV. And it has now produced a tool that I think is very valuable in the maritime domain, but also in other domains, the OT procurement vendor matrix. It provides a matrix of questions to ask your suppliers are they addressing the cybersecurity needs of your facility? And so it's not just a checklist, but it's for each security control, it gives real world examples why that is an important control for protecting the trustworthiness of the cyber infrastructure to support the organizational mission. So this was just published last month. This is the first revision. Please check it out. We're very interested in your feedback, your experience using this, this new tool. I want to make sure to advertise our annual NSF Cybersecurity Summit that TrustedCI hosts. We bring the community together each year to share our experiences addressing these cybersecurity challenges. We met in October at Berkeley Lab a few months ago, and you can find a link to our YouTube channel from trustedci.org/summit that'll include the presentations of the summit that just happened a few months ago. And we are planning this year's summit tentatively October 7 through 10 at CMU in Pittsburgh, PA. So the summit includes presentations and workshops and training. It's a very interactive event. And so if you haven't been, I encourage you to check it out. We organize our activities under a framework for developing cybersecurity programs for science called the TrustedCI framework. And it contains 4 pillars, not just the cybersecurity controls, but making sure that also your cybersecurity program has the resources to actually implement the controls, implement the governance and policies, and make sure that your cybersecurity program is aligned with the mission of your organization. We've developed this framework over recent years based on our experience working with NSF facilities and projects, input from the community, including a framework advisory board, and of course, not in isolation, but with many references in our documentation to other cybersecurity frameworks and other cybersecurity resources. These 4 pillars, you will also see them in the cybersecurity section of the research infrastructure guide, the RIG that Mike talked about this morning. So it's very compatible with the guidance that you receive from the NSF Research Infrastructure Office. And we've been now operating cohorts of facilities and projects adopting the framework. That includes a vetted self-assessment against the 4 pillars of the framework by the facilities members who are participating in the cohort, and then includes a project plan for improving the cybersecurity program of that facility under the under the framework. And then the graduates of the cohorts form what we call the Research Infrastructure Security Community, which comes together quarterly to share information about emerging threats and their experiences and their challenges. These threats are real. So got two examples there from Noir Lab and Alma, where they have responded and recovered from attacks to their facilities, and their sharing of their experiences has been very valuable, I think, to that community. And so keeping abreast of those threats to the facilities and how we're addressing them is a key component of this growing community. Our partnership with CI Compass is very important to TrustedCI. Again, as Mike said, a lot of wisdom in Mike's presentation this morning. Cybersecurity people should talk to the data management people. I mean, and we do, and so this partnership is about making sure that we're having those conversations. We're also two of the NSF Centers of Excellence, and so we have a lot of sharing about how we operate as effective centers of excellence, and that's also really valuable to us. Another valuable partner of TrustedCI is ResearchSOC. ResearchSOC is an organization that provides operational cybersecurity services to the NSF CI community, and they've now gotten their NSF startup funding, and they're now a subscription-based service providing those operational services that are very compatible with the TrustedCI framework for cybersecurity programs. And lastly, I'll mention our partnership with the Regulated Research Community of Practice that addresses those data regulations that have come up in our discussions this week, such as CMMC. And so that's a very vibrant community with a lot of experiences about implementing programs to address those regulations. So please check it out if that's new to you. And please keep in touch. So join our monthly webinars, check out our blog where you'll find out about our new documents. You can see the link to that OT vendor matrix. Join our discussion mailing list. And contact us anytime, info@trustedci.org. Thank you.
Great. Last but not least, we have Jamie Rollins. Come on down.
Hi, my name is Jameson Rollins. I am a senior scientist and the CDS Control and Data Systems software lead at the LIGO project. And I just wanted to talk a little bit about some new work we're doing in low latency data processing. And I also wanted to mention this data mesh concept, if people have heard it, because I think it's kind of relevant to this group. It's kind of an interesting idea. So just as a little bit of background, this is one of our most prominent events from LIGO, which we called GW 170817, which was our first binary neutron star observation back in 2017. And it was a truly exceptional event. We got really lucky in having two really exceptional events early in the advanced LIGO era. But this one is particularly noteworthy because of the involvement in so many other projects to follow up this event. It's like sort of one of the real true first multi-messenger observations. So the picture on the left is the sky localization. And you can see the green sections are the localization from just the LIGO Virgo detectors. If you fold in the Virgo detector, that shrinks it down to that red region. And then the diagram on the right is a complicated diagram. It's kind of an amalgam of a couple of diagrams from the multi-messenger paper associated with this event that shows all, or kind of a timeline of all of the observations that happened after our observation of the BNS, which is just truly remarkable for the number of other, telescopes that followed up this. And I'll note that sort of the first electromagnetic observation, I think, well, I mean, the top rows are some events from like gamma ray events from Fermi and Swift. And then the green dot is our first electromagnetic observation that identified the counterpart. And that's happened about 12 hours after our initial observation. But what I want to kind of draw your attention to is that block before the 12 hours leading up to that first event there's an incredible amount of science happening there. So we're really interested. The sort of interest we got in this event has really driven a lot of the science we're doing in LIGO since then. We're spending most of the effort, the human power in the project, I would say, in the collaboration, or not most, I don't know, that's hard to quantify, but a lot of effort to try to improve this system, to automate our sending out of alerts to the astronomical community. And we would really like to try to reduce the latency of getting these alerts out because of the just incredible amount of science that's in that first 12 hours. If we could get our alerts, I mean, hopefully within the next couple of observation cycles, we may be able to send out alerts before the GRB happens. We may be able to point telescopes before the GRB actually happens. So if telescopes could actually view the gamma ray burst as it's happening, I mean, that would be truly incredible. So that kind of motivates a lot of what we've been working on recently. So this new project that we've undertaken in the last couple of years is to try to improve our low latency processing infrastructure. And also just we're trying to update a bunch of systems that have been, I kind of mentioned this yesterday, that have been, we've been using computer systems that were developed 20 years ago, and we kind of duct taped and, gum to try to keep them going and to try to add new functionality to them to do this kind of low latency processing. And it's about time for a refresh. So we're kind of rethinking everything from the ground up. And so this is the low latency data stream processing, data delivery to the scientists in the control rooms and to everywhere else. We have a low latency data distribution system for the analyses that produce these events. We're probably not gonna, in the first phase, we're not gonna touch that, but this new system is gonna feed into that. And I'll kind of describe it a little bit right now. So this is just a very simple cartoon of the interferometers that are producing these large data streams of about, a quarter of a million channels roughly, with about 20,000 of those channels, what we consider to be fast channels that are kilohertz sample rate up to our highest sample rate, which is 16 kilohertz for the strain channel, the calibrated strain channel, which is the one that has the gravitational wave signal in it. And so that's the one that we're most interested, that's the thing that the analyses are looking in for the signals. But there's a lot of other information that comes from all of our auxiliary channels to do kind of detector characterization, data quality, and stuff like that needs to be processed around about the same time. And so all of that data goes from a data acquisition system into this stream processing framework, or needs to go into some kind of stream processing framework so that we can produce a calibrated strain channel and all of the sort of auxiliary information that we need for the searches to do the best analysis that they can. And so that kind of this middle region is the one that we're focusing on. And then the searches analyze that data in our computer clusters and produce these low latency alerts that go out into this new schema alert network to look for coincidence with other observatories like IceCube and stuff like that. So this is, we're still sort of prototyping this we're hoping to get a sort of working, beta product out by the end of this year. This is really another kind of quick diagram to show roughly what it looks like. We've got the DAC, what we call the raw data stream coming in from the observatories. Well, and this is kind of, I guess I should say that this is a little bit of an oversimplification, because these data streams actually, we multiplex multiple interferometers together. We have the whole worldwide network, which is really important. We have more interferometers coming online. So we try to get the data streams from all of the observatories together at one facility to do the searches. But this kind of stream processing framework that I'm talking about is happening at each of the LIGO observatories. And some of the other observatories are adopting the software that we are using, and some of them are doing their own sort of thing. But this is kind of the system that will work at one of our observatories. So the full raw data stream, that 250,000 channels, will go into a Kafka pool, and then there's something is sitting off of that Kafka pool, absorbing all of that data. Time series database, which we're looking at something called ClickHouse now. I've tried to put in the products that, the sort of products that we're using to kind of pipe this system together. And then that system on the right in the red will provide a service to which stream processing applications can subscribe to whatever set of channels they need. And then those stream processing processor applications can produce new channels that feed back into the system. And then, anything can get whatever set of channels it needs in a synchronized way to do the processing. And then this whole system will essentially feed into the low latency distribution network that actually provides the data to the search processes. So that's kind of an overview of what we're doing in LIGO, this new thing that we're putting together. And I'm very interested, anybody who's doing, just a really quick show of hands, which projects here have very tight latency constraints for the data processing that they're doing? Okay, so there are a couple, and this is really important for us. So I'm really interested in, in talking about that. But that was a little bit of a overly long introduction, because I wanted to talk about this really quickly, which is this data mesh concept, which we came across when we were sort of researching technologies for this system we're putting together. And it's a little, it's jargony, and it's talks about things in the way that they do in industry in the tech world, which is a little bit cringy. But there's some interesting concepts in here. And there's sort of these 4 basic tenets of the data mesh idea that you have. The basic idea is that you try to get away from putting all of your data into one central data store, where everybody, all the data goes into one place, and all of the consumers of the data get the data from that one place, where you have to have all of the centralized managed processing of the data or curation of the data, and kind of push that out and let different data sources manage their data sort of independently, but try to make some coordination in terms of how the products are made available to the end users. So the basic tenets here are this distributed domain-driven architecture, meaning that there's not a centralized data store. Each of the different domains sort of manages their own data as a product. Have it be discoverable, addressable, trustworthy, that kind of thing. Self-service data infrastructure, so the individual domains sort of serve their own data. And then this federated data governance, which means that there's some sort of centralized repository of which data is available where, so you know where to look for it. So this is kind of a little cartoon of how that might look. And the way that we're kind of embracing this is that instead of taking all of the data from all of the interferometers and putting it into one place, we're kind of trying to make infrastructure that each of our observatories will produce data into its own system, but then those systems are coordinated in terms of the, the schema to which the data is available, how you find data within each system, but then make it so that it's easy for the client to pull data from multiple sources in a, kind of in a nicely packaged way. So a lot of the technology that we're looking at, like this Aeroflight protocol, which is based on gRPC, has some of this kind of concepts built into it, where in the protocol, there's like an initial request for, I'm looking for these channels. And in the initial, you basically just make that request to whichever server is the closest one for you to talk to. Then that one says, I have these channels, I don't have these other channels, but I know where you can get them from. And then your request gets basically directed to those other sources. And then the client can essentially, get the data from all of those sources and multiplex it together and provide a synchronized stream back to the user. So I just kind of wanted to throw this concept out there because I think it's got a couple of really nice things that sort of mesh really well with the way that we're doing things in the gravitational wave community, where we're trying to make this really strong network of facilities that are all producing data, but eventually we need to get all that data to consumers together. And so we don't want to necessarily enforce that every observatory participating in the network, use the exact same data distribution system that we are, but if they can sort of build whatever data acquisition they want, data storage they want, but if they're public facing or scientist facing interfaces kind of conform to the standards that we outline, then it makes it very easy for the scientists to get data from all the facilities in kind of a unified way. So I just thought this was an interesting idea that sort of is well suited to our use case, but is maybe useful for other people to think about as well. That's it. Thanks.
Okay, great. We have time for one question.